Yes, okay, good. It's up there.
Okay, so welcome back. Before we start, just two brief announcements. So another reminder, there is a talk this afternoon, which is on the board here. And I'm meant to remind you that dinner tonight, the dinner starts at 7:30. Apparently promptly, we are asked to arrive for 7:15 at
The old kitchen.
sorry?
The old kitchen at Trinity College.
Old kitchen at Unity College. Okay, right.
Yeah.
So, and let's proceed with the scientific part of the meeting. So the next talk is going to be by Daniel Lesnick from Leeds, and he'll talk on determination of an additive source in the heat equation.
Okay, thank you very much, and good morning. First, I would like to thank the organizers for inviting me to participate at this excellent conference, following the events in the last 2 years, all held in the Isaac Newton Institute. I hope you can see this. I would like to show an example where there is some river pollution, apparently caused by sand, which is carried from downstream. But is it in fact a pollution caused by sewage disposal? That's one example of the source problems I would like to look at today. The other example is a picture which shows the effect of acid rain on a river as it happens. So in both cases, one can see that the problem of determining the sources of pollution in either rivers or lakes from water contaminant becomes of practical importance. Okay, so yeah, make it bigger. Thanks. So first, we have given some physical motivation for what we shall look at the mathematical modeling of an inverse source problem for the, in general, convection diffusion equation. But in this context, I will simplify it to look at the heat conduction equation. In the mathematical formulation, as given such, one would like to recover a source which may depend on both space and time, although it can depend also on the function, the dependent variables such as a temperature or a concentration. Dealing with partial differential equations, one of the main tools to use is Green's formula. Green's formula is for PDEs what Pythagoras theorem is for geometry, for example. So it is very useful in formulating the mathematical problem in an integral form. Then we shall look at the conditions for ill-posedness of the problem in terms of existence, uniqueness, and stability of the solution with respect to noise into the data, and show some of the typical results obtained by classical Tikhonov regularization method. And then all this framework is suitable for classical strong solutions. Later on, a least squares variational formulation for weak form solutions will also be proposed. And in that case, the iterative conjugate gradient method can be devised in the sense that the gradient can also be calculated explicitly. I should say that the problem we look today, it's a linear inverse problem, and therefore somehow the numerical implementation it's simpler, and we shall see some numerical results in this combined approach of inverse heat source problem. Okay, so we are not looking first at point sources where you can have a source which you want to determine carrying into the stream of water. We look for distributed sources, so these are classified as sources which deliver pollutants indirectly through some environmental changes. So imagine a fertilizer which is carried into a river by acid rain, and this will in turn affect the aquatic life. So if we are facing such problem, we'd like to mathematically model it, and as I said, we can use convection diffusion equation. There will appear the source of water pollution as a classified unknown source, which may depend on space, time, or on the concentration or the temperature if you work in heat transfer. Now, there has been a lot of literature, of course, in inverse source problems for various operators, elliptic, parabolic, and hyperbolic ones. Here we look at the parabolic case, and because of the non-uniqueness of solution, in general, one has to particularize the class of functions in which the solution is sought. And in general, we look either at functions which depends only on space, or depends only on time, or depends only on the dependent variable t. This analysis is a first step maybe towards looking at a more general case when the source depends on both space and time, but it is doing it in an additive fashion. Later on, one can imagine how to do it in a multiplicative fashion. But that's the aim of this investigation. So I would like to write this formulation on the board because this is the problem we want to solve. So we want to find a triplet consisting of the temperature solution U, some component of the source F1 depending on X, and another one depending of T, satisfying say parabolic heat equation, linear one, in some solution domain. We can have 1 or 2 or 3 dimensional domains omega. The time interval is from 0 to capital T, subject to some initial condition at time t equals 0, some boundary conditions, let's say on Dirichlet type. These are specified functions. When the functions G0, F1, G1, F2, G2 are all given, this is the set of the conditions for the direct problem. However, in the inverse problem, we don't know these two components, so we need to supply additional data, and we can have it of various types. We can have a pointwise measurement of the temperature. That's what is done in practice. If you install a thermocouple inside a plate, then you measure the temperature at an interior point in time. But this is not very suitable for mathematical weak 4 formulation, so we need in fact to average this with some weight function W1, which is given, and integrate. This usually is called the mass or energy of the system. It's a quantity which is measurable. Omega 1, it's a given function, but if you think that omega 1 is a delta function centered at x0, you can recover the pointwise measurement before. So this is a temporal measurement at a fixed sensor location in time. So you would hope in principle that the mapping H of t will determine the components F2 of t. And then if you want to hope to get f1 of x, you need some space-wise measurement. So then we would have the average temperature measurement, in this case, the integral from 0 to t, some function, call it g of x. And it's simple to remark that you need an extra fixing condition if you want to make this this combination unique, because you can add a constant and subtract it, so you need to fix a condition here. Say f1, it's a given number, or say the integral it's another given number. So in those two cases we shall look at the inverse problem. Okay. So the first case we look at is trying to see what we can say about the solvability, the unique solvability of the problem. In certain spaces, these are Holder spaces of classical functions. There are certain conditions which they need to be satisfied, but although they look complicated, the first one, A1, are just regularity conditions for the given data. This is the initial data U0. This is the boundary data. This is the source G0, which you can take it 0. In fact, this is known, but let us put it there. This is the measured data G and H, some regularity in higher dimensions. The second condition are just compatibility conditions in order to avoid singular solutions, which are usually needed when you solve in a classical sense the problem. And the final A3 conditions are conditions required for the identifiability. Of course, if you take G1 to be 0 or G2 to be 0, there is no hope you can get these coefficients in front of them. But they are just some simple conditions which are easily possible in practice. Then there is possible to get local solvability of the function in classical Holder spaces. Now, even so, even the problem satisfies the first two conditions in the Hadamard sense for well-posedness. There it's easily, you can find an example showing that the solution is unstable with respect to small perturbations into the data. And this is just a one-dimensional example in a finite slab of length pi. If you pick up x0 to be the midpoint, then you can define a sequence for all integers, positive integers n, in this form with some given data. But what was of interest are the sources f1 and f2, which they look like square root of n times a sine, square root of n times a cos. And let us look at the input data. So input data f1, 0 is 0, h2, it's a sine nt over square root of n. This goes to 0 as n goes to infinity. G of x also contained at the denominator's power of n. So both data h and g, they go to 0, whilst you can see the output, the solution goes to infinity oscillatory. So this is just a classical instability. Small errors into the input data h and g cause big errors in the output. So we have a problem to deal with. Although we haven't proved, it is believed that if you have stronger assumptions on your input data, such as you have continuity in the derivatives for h and g, then we can restore some stability. So that's also proved. Some of the technique used by Randall in his paper can be used here, probably with some semi-group theory as well. I mentioned about the employment of the Green's formula, and remark that the operator I choose is a linear one in the leading part, if you have some space-wise dependency in terms of a thermal conductivity, you'll have to use some Green function based on parametrics or something else, but it is convenient to write down explicitly the fundamental solution, the free space Green function in this form, where h is just a Heaviside function, which is introduced only to say that this square root makes sense for t greater than tau. And then you can recast the first partial differential equation, which was of a differential form, into an integral form as given there. Here we have an integral from 0 to t over the boundary d omega from the reciprocity gap between the fundamental solution G and the Dirichlet-Neumann data for the function, temperature function u. This is a volume integral due to the presence of the heat source. So this is where the heat source appears. It looks like now a Fredholm integral equation of the first kind. This is just some additional domain integral due to the initial condition, which you can take it 0 if you want. So we can recast the problem in this linear form. If you recognize this as a Fredholm integral equation of the first kind is clearly ill-posed. Let us look at some simple technique to solve for both functions f1 and f2. Here t is the transpose of a vector, x is some matrix. So upon discretizing the previous integral equation, using for example boundary element method, reduce the problem to solve an ill-conditioned system of linear equations. Here the right hand side, it's a vector which may contain some noise epsilon. So this has the noise. We look at how bad ill-conditioned is the matrix X, and we have calculated with respect to the number of boundary elements 20, 40, 80, and various locations where you put the sensor, the condition number. So one thing to remark is the position of the sensor is not important, so these conditions numbers are of the same order. But if you look on the horizontal line, you can see that as the number of elements, the dimension of the matrix X increases, then the condition number will increase as well. So this is getting bigger and bigger, and therefore we need to deal with this ill-conditioning somehow. This is how fast the singular values, they decay to 0, and these are various mesh sizes, but you can see towards the end they decay like 10 to minus 4 there. So one way would be to truncate it, maybe there. But we could use classical Tikhonov regularization method as written here. You have the residual and then some additional penalty terms. The first one penalizes the function, the component f1 of x, and the second one, the component f2. R1 and R2 are just some regularization matrices, which they can correspond to 0, first and second order, depending on the smoothness required. More importantly are these parameters lambda 1 and lambda 2 to determine, which are the regularization parameters. Now, it's enough that it's difficult to find one of them when when you have only one term, but for two of them. So to get two of them, it's quite difficult in practice. However, we shall look at some results. We perturb the input data with some 1% random noise. And the first thing is shown here is a generalization of the so-called L-curve method. It's called the L-surface method. This is because you have two parameters to identify. Therefore, you have to plot a graph of a surface. On one axis is the residual, and on the other two axes you plot the penalized terms. Actually, there is a change in notation. R stands for F1 and S stands for, no, S is for F1 and R is for F2, but it doesn't matter. You can see that you can get something which looks like an L surface. This is a projection onto the base plane. And this may look like some L curves. And you can pick up a whole valley of points of parameters lambda 1 and lambda 2 for the corner of that thing. Let's see how good we obtain the solution for that particular choice. Here the exact solution, this is the component f1 of x. It says of x because that's how it was in the initial paper, but anyway, this is f1 of x. So the exact solution is I think it's a parabola, that one, the continuous line. And these are the numerical solutions we obtain with various values for the regularization parameters, lambda 1, lambda 2. First, we take them equal, and we use an L-curve criterion, which turns out it gives a value of 10. And then the dotted line, the dashed line, produces this solution, which is far from the true one. Then we use this L-surface method, where you allow lambda 1 to lambda 2 to be independent of each other, and you get 10 and 1 some typical values. So we got this particular solution. However, this is not optimal, neither of them. In fact, the best solution we could get was this one, which is obtained by trial and error. So there is room for improvement in the choice of multiple regularization parameters. Research is going on, and people still publish papers on various things, but it's a difficult issue. Okay, so now we remark that in practice and also in mathematical setting, it's difficult to deal with pointwise measurements. And then we use a weak formulation, a variational formulation, which will be based on minimizing the gap between the measurement and the computing data. So in that case, I rewrite the problem. Now the function u is sought in a space of functions as usual. F1 and F2 and majority of the other functions are in L2 setting for simplicity. And we produce the measurement h of t as the integral of omega 1 u. And we also generalize this second measurement to put away there omega 2 of x. This is done like in Prilepko's papers or books, because he wants to see that if you take an omega 1 approximating a delta function centered at x0, and maybe this one, I think it's a mistake here, should have been t. So omega 2 of t centered at some point t0, then you get pointwise measurements as before. Anyhow, in this case, you can rewrite a simple operator from the space of L2 in omega times L2 of 0t, components F1 and F2, going into the measurement. This is g of x and h of t, and you can show that this is compact, and therefore the inverse is unbounded, so the inverse problem becomes ill-posed. It's useful always to construct the adjoint, which is just the backward operator but with the minus sign, so this makes this problem well posed. And then the Green's formula, which is used to derive also the gradient of the least squares functional, holds in this form. So with these classical tools, we can construct the variational formulation, which minimizes the gap between the measured data h and g and the computed ones. This is the normalization condition to make the solution unique as well. And then it's simple exercise of calculus to show that the function is Fréchet differentiable and the gradient can be evaluated explicitly. Here it has two components because f denotes a pairwise f1, f2 vectorial function in this space. And well, this is the adjoint problem producing the corresponding gradient. Now we have the conjugate gradient method as a suitable tool for implementing the iterative minimization, which was previously derived. So the first step is to initialize the iterative process. We can pick up an arbitrary initial guess, f0, and then the first step is to calculate the corresponding residuals, and then solving the direct problem, we can generate the gradient, the function which we want to minimize, and later on the gradient itself. So we can work out the gradient R0 in this form, and this is explicit form because all the quantities are given. Psi 0, it's obtained by solving the adjoint problem, which is well posed with 0 initial data, but the source terms, they are present in this form. Notice the weight term omega 1x and omega 2 of t, they become present into the right hand side as a source term. And here they are just the components which are explicitly computable. And then we obtain the first directions of the search in the conjugate gradient method. And then we generalize this. We move at an arbitrary iterative step. So for n from 0, 1, 2, and so on, we solve the problem at the nth iteration step, and it consists of the terms which are written on this form. Again, 0 initial data and boundary data, and here the source terms containing x and t. Now, to solve all these problems numerically, you can use either boundary method or finite element method. We shall perform two-dimensional computations later on. So the choice of solving all these well-posed problems will be based on finite element method this time. Once you have obtained the direction search, you can also determine a parameter beta n, which will enable me to move from one iterate to another. So this is classical fn plus 1 equal the previous solution plus a direction search in a certain sense. We can also calculate the residual and move forward. So this is what happens at the next step, n plus 1. So in that case, we have the previous quantities as calculated, and also we need to solve again the adjoint problem. At each iteration in general, we only need to solve a direct and an adjoint problem. So the procedure, it's quite rapid and fast. And then we can update the direction search with a classical method. This is just a reiteration of the methods for vectorial functions as given in classical books like Hanke or Engel and Neubayer and the others. What is important with the regularization procedure, because it's an iterative one, you may ask where is the regularization hidden. And in this case, stopping the iterations and at an appropriate threshold plays the role of the regularization parameter. And this is classical discrepancy type, Nemirovsky type discrepancy principle, where you stop the iterations at the level where the residual becomes less or equal than the amount of noise with which the input data is being contaminated. Here, delta 1 and delta 2 stand for the noisy measurements of the functions g and h. So if these are subjected to certain amounts of noise, 1, 2, or 3%, let's say, then you can calculate this quantity. Sigma is just a number strictly greater than 1, which nobody knows how to choose it. But anyhow, you just pick up the first or around the first iteration number for which the residual becomes less than this quantity. If you stop before that, you over-smooth the solution, you get a stable but inaccurate solution. If you leave it too long, then this becomes unstable, so you go into the other. So this is just the common semi-convergence phenomenon, and the conjugate gradient method has a regularization effect. Now, there could have been another type of regularization. If we look backwards, and we have tried that, you could have directly add Tikhonov regularization terms into this expression as well. So we could have had, apart from these three terms, which they impose the measured data H, G, and C0 in a L2 sense, we could have added to this expression lambda 1 norm of F plus, lambda 1 norm of F1 plus lambda 2 norm of F2, the same we did before as explained. In that case, it's possible. You can leave the conjugate gradient to run forever up to convergence is achieved, but then the problem is still how to choose lambda 1 and lambda 2. So both methods we have tried, they produce very similar results. So in some sense, especially for linear problems, stopping the iterations according to Nemirovsky criterion is given there, it's enough. So let us look now at some numerical results. This is just a simple test example. We have performed many others. This is a two-dimensional unit square geometry over a time interval of 1 unit. There is some analytical solution for the temperature available. We pick up the weights for simplicity to be 1. And then working it out, we can generate the sources, G0, F1, and F2. In particular, we will look at what is the value of F1 and F2, and we determine the source G0 such that we can have any example we wish. G1 and G2 are just some given function. We use some finite element method. The initial guess, it's arbitrary, and we take it to be 0, 0 in this case. Delta 1 and delta 2 will stand for the amount of noise with which the input data is contaminated. N star will denote the regularization parameter where you have to stop the iterations before the residual becomes too small. And that's the first N star for which the residual becomes like that, sigma about 1.1 times the amount of noise. So let us first look at an example where the functions to be retrieved, F1 and F2, are discontinuous. And this is a severe test example, nevertheless. So it's a step function which is 1 in this square of size 0.4 within the unit square domain. And the F2 of t, it's a function of a single variable, which is 1 between 1/3 and 2/3 and 0 otherwise. So we have discontinuities in F1 and F2 at the core, at the sides of this square, and at the points 1/2, 3, 2/3. So, okay, this difficult example. C0 turns out should be 0.16. And then in this table, we produce the results. And N star represents the number of iterations with respect to the noise level. So of course N star will depend on the amount of noise. The smaller is the amount of noise, the larger it's N, as you would expect. In the limit as delta 1, delta 2 are 0, N star will be infinity. But of course in practice never happens that way. But let us take first a small amount of noise, then a medium amount of noise, and a big amount of noise. The number of iterations, well, for this particular example, they decrease like that. And these are the errors, the accuracy errors between the numerical and exact values in the L2 norms. And one can see that, if you want, as the amount of noise decreases, then the error tends to 0. And the same is happening in this case. The accuracy in retrieving the time component seems to be better than that in retrieving the space component. Somehow you expect that because F1 is 2-dimensional, this is 1-dimensional. J of fn star represents the value of the objective function as we stopped it, and one can see small values. Ideally, there will be 0 in the case of error-free data, but depending on the amount of noise, there is a good fit between the measured and the computed data. So these figures present a comparison between the exact solution. That's first for the spacewise component of the heat source, F1 of x. So remember, it is a step function, which it's 1 within this particular square 0.3, 0.7. The rest is 0. And this is the approximate solution, the best we could do even when we have no noise in the data. So there is, of course, some numerical noise because we don't commit the inverse crime. So we use the analytical values. So there is some numerical noise, and then we get this recovery. When you put real random noise, then the recovered solution is nevertheless stable. It's smooth. Of course, it has some discrepancy between the exact one and the numerical one because you have some noise into your input data. Okay, but it's stable. The previous graphs were for the space-dependent component. Now, okay, this is also space-dependent component, and this is the time-dependent component. This is just a slice through the previous two-dimensional graphs. So if you take a slice, you fix x1 to be 0.5. So we slice through the middle. Then we can plot the source as a function of x2 from 0 to 1. This is the exact solution, which is the step function. And the numerical solutions obtained with various amounts of noise, 10 to minus 2. Okay, let's say this is 10 to minus 2. Too big, too large amount of noise. I only get some, poor reconstructions. But for smaller amount of noise, 10 to minus 3 and 5 times 10 to minus 4, the result seems better. And this is the recovery for the time-dependent component. Again, the exact solution is this step function. And this is just some recovery of the numerical reconstruction for this discontinuous input. I only show the results for the most difficult case. We have in the paper smooth examples and piecewise smooth examples where the reconstructions are much better. So that's been reported. Another interesting thing to look is that, and this is valid also for the Tikhonov regularization previously, is that if you try to somehow to get better results for F1, you get worse results for F2, and the other way around. If you try to get this one better, then you pay the penalty. This becomes worse. So there is a balance between F1 and F2 in this additivity form, which is interesting, and it makes the problem non-trivial for further research, such that if you can get them both simultaneously correct, that would be good. But it tends to be that if we have any stability estimates, there will be somehow balancing, and should be a compromise where you get both of them, the optimal numerical reconstructions. Okay. So I will conclude into saying that we looked at an initial attempt to try to move from the case when the function depends on either space or time. So we have an additive combination, linear combination between a space component and a time component. The problem is still posed, but it's linear, and we have many tools to solve it. In particular, it was interesting to look at both the strong and weak formulations, for which we were able to prove some solvability results, as well as calculating the gradients. Numerically speaking, we could apply non-iterative classical Tikhonov regularizations, but here the issue is how to choose a couple of regularization parameters, lambda 1 and lambda 2. And iterative methods, they seem quite powerful, and the best would be based on conjugate gradient method. You have slower algorithms such as Lamb-Weber method as well. But so the next step is to move to investigate the multiplicative heat source case. So in that case, you'll have the product between f1 of x times f2 of t. Okay, this will disappear, so you have. And in that case, obviously, the problem becomes nonlinear. It's still ill-posed, as in general with inverse problems. And the situation will be more complicated, nevertheless. Thank you. Yep.
Have you tried to investigate H1 convergence? So you focused on L2 convergence. Have you tried to investigate in other spaces?
We haven't looked at other spaces. We just, I mean, the only hope we have here was to try to get some stability. I mean, in this sense. So if we have the data in H1, H, and this is in H2, then I think this holds. But I haven't proved this. But, yeah. But as far as the conjugate gradient method, yeah, probably that could be employed as well. Much closer to practice, we have L2 spaces in general. Yep.
If you can go to the last, or almost the last, just curiosity, is there, yeah, it seems that the first one is very smooth and the other is highly oscillating. Is there a reason for that?
Yeah, that's also I could remark. Yeah, that's how I also could remark. There is, yeah, this is over smoothing and this is under smoothing. That's what. But this is what the discrepancy principle gives you for this problem. I don't have a major. I mean, for the smooth examples we've tried, we don't have this. We don't have this issue. But for this one, if you don't go to solve problems which are difficult and closer to practice, probably you will be misled to believe that the method is perfect in that sense. But this just shows points where I just mentioned. Maybe this is over smooth, this is under smooth. So it should be something in between. Maybe the discrepancy principle is not the best in that case. It's not optimal.
No further questions?
Thank you.